In this video, we're going to look at concavity and the second derivative test. The second derivative test is very similar to your first derivative test, which is your increase-decrease test, because you can still find local maximum with both tests. The only difference is the second derivative test is going to tell us a little bit more. It can tell us when a function is curving up or curving down, and that's called concavity. More specifically, when a function is concave up, f prime is increasing there. If our function is concave down, f prime is decreasing there. Now, if you take a look at the pictures on the left side of your two functions, we have f and we have f prime below. Now, between -2 to 0, we have concave down for f, and corresponding to that, f prime is decreasing. From 0 to 2, f is concave up, and corresponding to that, f prime is increasing. Now, the test for concavity states that if your double derivative is positive, then f is going to be concave up. If f double prime is negative, then f is going to be concave down on that interval. In summary, if the second derivative is positive, then the first derivative is increasing, and the original function is concave up. If the second derivative is negative, then the first derivative is decreasing, and the original function is concave down. So there are a few guidelines that you can use to help determine concavity. The first thing you're going to do is find the second derivative of the function. Then you're going to locate where f double prime is 0 and where f double prime of x is undefined. This is very similar to finding critical values. Then we're going to make a sign diagram for that second derivative using those x values you just found in step 2. In the areas where the second derivative is positive, then f is concave up. If f double prime is negative on that interval, then f will be concave down there. Let's do an example of this now. So the first thing we're going to do is find the double derivative, but before we can do that, we need to find the first derivative. So we're going to use our power rule here. This is 12x squared plus 42x plus 36. And then now we'll do the double derivative, which is 24x plus 42. Now take a note that this function is never undefined because it's a linear equation. Our second step is to set f double prime to 0 and then solve. So I'm going to subtract 42 on both sides and then divide both sides by 24. So our simplified fraction is going to be -7 over 4. Our third step is to create the sign diagram for f double prime. And the only critical point we found is -7 over 4. So we're going to plug in values on the left side of -7 over 4 into f double prime, and then we'll do the same thing for the right side. So let's pick a really large negative number. Let's say 100, -100. If we did that, we're going to have a very large negative number as our first term, plus 42. That means overall, this interval is going to be negative. Again, on the right side, if we pick a very large positive number, we're going to get back a really large positive number. So again, you're plugging in values on either side for your interval into f double prime. Now, according to our double derivative test, this will tell us about concavity. So if f double prime is negative, then that means we're concave down for f. And if f double prime is positive, then f is concave up there. So in summary, f is concave down on negative infinity to negative 7 over 4, and that's because f double prime is negative here. F is concave up on negative 7 over 4 to infinity, and that's because f double prime is positive here. And then we're done with that question. Let's do another example. Again, we want to figure out what intervals f is concave up and down, so we're going to use the same 3 steps. The first step is to find the double derivative, but again, we need to find the first derivative before we can do that. Because we have a fraction or a function over function, we're going to use the quotient rule. So if you take the derivative of the numerator, this is going to be 2x, then you leave the denominator alone, minus, leave the numerator alone, and then take the derivative of the denominator. All over the denominator squared. Before we continue, we should probably simplify this. So I'm going to factor out the 2x. And then simplify. So we have negative 10x all over x squared minus 4 squared. Now we'll find the double derivative. So we'll take the derivative of the numerator, which is negative 10, leave the denominator alone, subtracted by negative 10x, and then take the derivative of the denominator, which we are going to use a chain rule for. So this is 2x squared minus 4 multiplied by 2x, all over x squared minus 4 to the power of 4. And if we do take the time to simplify this, you are going to get 10 times 3x squared plus 4. Okay, now our second step is to set this equal to 0 and to see if this thing is ever undefined. And it will be undefined if x is plus or minus 2, because we get 0 in the denominator. Now to set f double prime to 0, we only need to set the numerator to 0 for this to happen. And if we check this out, well, this is never the case, because otherwise we need to solve for this, and we can't take the square root of a negative. I mean, we can, but we just don't want to use complex numbers right now. So the only values we're going to consider is our plus and minus 2 when we do our sign diagram. So we're going to plug in numbers into f double prime so we can do a really large negative number. And if you do that, we're going to get a positive number back. If you put in 0 in here, you're going to get a negative number. If you put in a positive number into f double prime, you're going to get back a positive. So that means f double prime is going to be concave up here, then down, and then up. So to summarize this, f is concave up on negative infinity to negative 2 and 2 to infinity, and that's because f double prime is positive here, and then f is concave down on negative 2 to 2, and that's because f double prime is greater than 0. Sorry, smaller than 0, so I'm going to concave down. And that's it for that question. Now we're going to look at points of inflection. So points of inflection is whenever the function goes from concave up to concave down, or concave down to concave up, and so on. So these are examples of different inflection points that you could see. We can find these inflection points as well. And this happens if f double prime is 0 or if f double prime is undefined. And we can look at the concavity in our sign diagrams to determine if we have an inflection point there and what type of inflection point do we have. So the first step you're going to do, like the other questions, is to find f double prime. So we're going to find f prime first. So this is 4x cubed minus 12x squared. Then f double prime is going to be 12x squared minus 24x. Again, if you take a look at this is never undefined. This is a polynomial, and more specifically, that's a quadratic. So then now we're going to set f double prime to 0 and solve for x. So I'm going to factor out 12x here. And then our x values are going to be either 0 or 2. So those are the 2 points we're going to use when we're finding our sign diagram. So if I plug in a -1 into f double prime, we're going to get a positive number back. So for example, if we had -100 squared, that's a large number, times -24 times -100, that's also a large positive number, so we're getting it back positive here. Then we can pick 1 for the next interval, that's 12 minus 24, that's negative. And if you pick a very large positive number here, we're going to get back a positive number. So that means f is concave up, concave down, then concave up. So the points of inflection are x equals 0 and x equals 2. And we can tell they are inflection points because we go from concave up to concave down, and then concave down to concave up. So the points of inflection are at x equals 0 and x equals 2. Since f double prime changes from positive to negative in the first interval and negative to positive on the second one. Now we're going to look at the second derivative test. Now the second derivative test is good for finding a local max and min, just like your first derivative test. The only difference now is we're going to use a second derivative to help us determine those local max and mins. So the condition to use the second derivative test is we need to find f prime of c equals to 0. And then the second derivative of f will be in the open interval with that c. So if you get the double derivative to be positive at c, that means you have a relative minimum there. If your double derivative at c is negative, then that means you have a relative maximum at c. But if f double prime of c is equal to 0, then this test fails. So that means we don't have enough information to determine if f has a relative maximum, minimum, or doesn't have anything. In that case, you have to use your first derivative test. So let's do an example of where we are going to use our second derivative test. We are given f. Our first step is to find f prime. So using our power rule here, we can differentiate f. This is going to be negative 15 x to the power of 4 plus 15 x squared. Now, if you look at the condition again, we need to set this equal to 0 and then find our critical points. So if we set this equal to 0, then we're going to get x is equal to 0, 1, and negative 1. Now we want to find the second derivative. So if we differentiate f prime of x and then factor it out, you will get negative 30x to x squared minus 1. Now we're going to look to see if you're going to have a positive f prime of x at 0, 1, or negative 1 to determine if we have a minimum, and if it's smaller than 0 or negative, then we're going to get a maximum there. So now we're just going to evaluate f double prime of 0, f double prime of 1, and f double prime of negative 1. So if you were to evaluate f double prime of 0, we're going to get 0 back. So this doesn't determine anything. If we evaluate f double prime of 1, we're going to get negative 30, which is smaller than 0. So that means that we're going to have a relative max here. And because it's negative, that means we have a concave down graph at around that place. For f double prime of negative 1, if you evaluate this, you're going to get 30. This is a positive number. That means we have a relative minimum. And then we're going to have concave up there. So now we just need to state our final answer, that we're going to have a relative minimum at x equals negative 1, and that's because f prime is 0. So that was coming from our very first step. We need to make sure that x equals negative 1 is a critical point. And the other reason we know we have a relative min there is that our double derivative is positive. Then we have a relative max at x equals 1. And we know this because, again, it was a critical point when we found our first derivative, and f double prime is negative there. Now, just one last note before we end this video. You can use the first derivative test or the second derivative test to find your local max and mins. The only time that you might want to use the second derivative test is how the question is phrased. So if you're given information that has double prime, then you can use the second derivative test because you're going to have enough information. However, if that's not given to you, the first derivative test can also be used. And that is all for this.